another process. Then these processes need to communicate with each other. So if it is waiting for another one, they need to communicate. This communication, this is referred as inter-process communication. So communication between two processors, right? So that is known as inter-process communication. So this is very important in operating systems. From the following section, you'll be able to learn basic principles in inter-process communication and the concepts behind. So we'll talk about mutual exclusions, NFO, and monitors. Those are the three terms you are going to learn. So first we start with principles in IPC. There are three main issues associated with inter-process communication. Let's see what are the issues in inter-process communication. Okay. So firstly, there should be a way to pass information from one process to another. That's the basic idea between inter-process communication. So there should be a way to pass messages from one to another. Secondly, it is needed to make sure that two or more processors do not get into each other's way when engaged in critical activities. What does that mean? So when you communicate, there are critical activities. So if you block a critical activity, whole computer might get stuck, right? Therefore, they should not block critical activities unnecessarily. For example, if one process blocks the CPU, it is affecting everything. Or if it blocks critical areas of memory, like that. Critical means you need those areas for other process to execute. Lastly, the third one, proper sequence needs to be present when dependencies are present. So when there are dependencies, so if one waiting for result of another, right? So we need to make sure proper sequence of execution. So if it is in wrong execution, if we implement the process which requires output from another earlier, then it will waste resources, right? So operating system must identify the proper sequence. So first we are going to understand.
Sir?
Yes, any problem?
In above mentioned, secondly, you said, can you scroll up? In secondly, you tell two or more process do not get each other when engage critical activities. Is that there are A process and B process. Some B process output want to for A process, and otherwise we think in the C process. So A process and B process do their works, not depend for C process. That means for
yes,
that
should not block C process. No?
Okay, sir.
If A is waiting for, let's say B is waiting for output from A.
Okay.
Right? So until A process, then B cannot execute. Okay. But if B is holding a resource required by C.
Okay.
Right? So C is a critical. the resource is a critical one, shared by other processors. So if B is holding that activity, others cannot execute, right?
Okay, sir.
Right. But like that, you can ask any question, not clear. So we'll see different issues we encounter first. First one is race condition. Okay. In some operating systems, processors which work together may share some common storage that each can read and write. Let's say you share a Word document among your team members or group members. Let's say 5 of you sharing the same document where you need to edit, right? So time to time you need to read the document, write it, and so on. So it is in the common storage. So this common storage can be the main memory or somewhere we store, right? So shared file. So let's take a simple example to illustrate how this inter-process communication works. So if we are sharing the same thing. So if we are sharing a file, right? So when a process wants to print a file, it enters the file name in a special spooler directory. So spooler is so let's say if you want to write something, if the printer is sharing one, there's something called spooler. So there are many persons accessing the same printer from this side. So they are sending print jobs. Let's say your computer lab sharing one printer. So few students sending printing requests. So normally there's something called spooler directory where they hold things not printed yet. Then, so when a process wants to print a file, it enters the file name in a special spooler directory. Another process, that means another user, the printer daemon periodically checks whether there is any file. Sorry, this printer daemon is from the printer side. So if printer is this side, it is frequently checking what is available, right? So something called printer daemon periodically checks whether there is any file to be printed. If so, it will print them and then removes their names from the directory. So printer side, it takes one file, then print it and remove it from the directory. So that is what printer daemon is doing. That is print. Let's assume the spooler directory has a large number of slots, numbers 0, 1, 2, and so on, like this side. Each one capable of holding a file. So each location, each number can hold one file. And there are two shared variables called out. This is one variable out, right? And which points the next file to be printed in. So in this case, out is 4 means, so printer can print ABC, file name ABC from the location 4. Which points to the next file to be printed, and in pointer in is another variable which points to the next pre-slot in the directory. So in this case, next pre-slot is 7, right? So next to print is this ABC, the location 4, and the in slot is the next available empty slot. If someone wants to send something, they can insert to in location. Okay. Next available free slot. Let's assume now process A and process B want to give a file for printing simultaneously. That means at the same time. So user A and user B send in files. So both are trying to access the next available slot, right? So you can see the situation in the figure. So operating system must decide what to do now. Okay.
Okay.
Let's say what will happen. When process A reads in and stores the value 7 to a local variable called next free slot. So process A has a local variable. Before sending it, what it does is it checks the printer spooler directory and get the next available free slot and store this one in its local variable in process A. So it read this location and store the number 7 value of in counter in its local variable, right? And then so next free slot. Just then clock interrupts and the CPU decides the process A has run long enough and need to switch to process B. You know the CPU side, it's a time sharing now.
Yes.
So yeah, process A trying to print, but once it has read the variable into its local variable, CPU decided to stop process A and give the chance to process B. Now what will happen? Process A is blocked by the CPU. Now process B inactive. Right? Therefore, process B also trying to print something. So it is also accessing the spooler. Again, reads in and also gets the same number because it is still empty. Process A haven't sent a file yet, no? So still encounter is 7, right? Then it too stores the same value in its next free slot, the local variable. Right? Now this local variable is in process B. Earlier local variable was in process A. Now process A local variable holding the value 7. Process B also now read the same value and store it. Then at this instant, both processors think that the next available slot is 7. Right? So both processors not send the file yet, but before sending it has to read the location now. So both hold in the location 7. So process B continues to run and store the name of the file in slot 7 and updates into 8. So update in counter, the in variable to 8. Now process B can read slot 7 and update. Where's the in variable? It is here, right? So now process B trying to send a file, therefore it update this to increment 1, pointing this to this one, because process B trying to send the file to 7. Right? So in counter now value is 8. Then it goes off and does other things. Okay. what will happen later on? Eventually, process A runs again when it gets the chance, CPU. So it checks the stored value starting from the place it left off. It looks at the local variable and writes its file name in slot 7. Okay, so it is sending the file for printing into slot 7. Erasing the name that process B just put there. So before that, now process B sends something and update the encounter to 8. Now what will happen here is process A sending another file to the same slot. So it will erase the earlier one sent by process B. Okay. Then what will happen? Then it computes next free slot as 8 and set encounter to 8. Okay. Now, as the spooler directory is internally consistent, printer daemon will not notice anything wrong. So this will happen in process side. They are sending files. But a spooler daemon printer side, it doesn't know anything about it. It just reading from counter and printing. Okay. So you see the problem. Spooler directory is internally consistent. Printer daemon will not notice anything wrong. But process B will never receive any output because request from process B is replaced by process A. So situations like this. So you see the problem. Huh? So printer does not notice this has happened. So situations like this, where 2 or more processes are reading and writing same shared data. And the final results depend on who runs precisely when is called race condition. So no one knows who wins, right? So we have explained it for 2 processors, but sometimes 5-10 processors will do the same thing, erasing the previous one and put their own thing. So no one knows who will get chance. Certain processors get erased, so certain files which needs to print. Okay, so this is one of the problems we need to address. This problem is known as race condition. Okay, so we should know what kind of problems can occur. So first one is race condition. Okay, I hope it's clear for you all. Unfortunately, it's difficult for me to draw diagrams and explain, but I hope it is clear. Right? So if 2 or more processors trying to access the same location and update it, so the previous one get deleted and so on. Printer doesn't know about that. Whatever available finally, whenever it access will get print, others lose, others not get it. Right? So then the next problem, earlier you asked the question about critical region. So we'll talk about critical region now. What is critical region? Problem of avoiding race condition can be formulated in an abstract way. Part of the time, the process is doing an internal computation and other things that do not lead to race condition. So only certain actions only lead to race condition. If they are independently running, no problem. But sometimes the process may need to access shared memory. Then only we get this kind of problem. Shared memory or shared files, which lead to traces, right? That part of the program where the shared memory is accessed, we can name it as critical region because only that part causing this problem or critical section. Okay. Therefore, to avoid race conditions, we have to make sure no two processors should access the critical region at the same time. So, in practically, we take one example. It is like a toilet. If there's only one toilet available, and we are having a class, so time to time, persons wants to use the toilet, right? So we know no two persons are allowed at the same time. Therefore, we can mark it as critical region. So how you make sure only one person get the chance? So same concepts you can apply here to avoid race condition. So in order to have a good solution, 4 conditions need to be considered. Four conditions. Let's see what are those. We have to make sure no two processors may be simultaneously inside the critical region, right? In your program, when you mark a critical region program or your operating system, so no two processors simultaneously inside the critical region. This one condition we have to make sure. Second one, no assumptions may be made about speeds, so the number of CPUs available. We can't make any assumptions about, okay, this process take this long, right? When some person go to toilet, you can't assume, okay, you are allowed only 30 seconds or 1 minute. We can't do that. Similarly, operating system, the processors, we don't know how long will it take in the critical section. Okay, that's the second condition. Third one, no process running outside its critical region may block other processors. No process running outside its critical region may block other processors, because if you block another process, it will make some other problems. And the fourth condition, no process should have to wait forever to enter its critical region. What does that mean? If some process not getting a chance to use it, so you have to avoid that situation also, right? So everyone should get a chance. All the process must get a chance. So we have to make sure, if we are providing a good solution, we have to make sure those 4 conditions are achieved. Okay, if it is a good solution. Sometimes you may forget 1 or 2 and have a certain solution. So now you got the idea about the problem. First, the problem is race condition here. So avoid that, we mark a portion called critical region. To have a good solution, we have to meet those 4 conditions. Okay. So let's see possible method of implementing. So first, we have to make sure the condition called mutual exclusion. Mutual exclusion is some way of making sure that if one process is using the shared memory, or you can call critical section, the other process will be excluded from doing something there. The Others not allowed to use this shared memory. Others not allowed to update this shared memory if one process is using it. Okay. So mutual exclusion with busy waiting can be implemented in several ways. So normally we implement this using busy waiting. If I take another example, let's say you are on a call, your mobile phone. So if another person wants to call you, now your phone is now like a critical section. Only one person can access it at a given time, unless it is a conference call. now if phone is engaged, the other person, you can send a busy waiting message like engaged on. Okay. So it is busy waiting, can be implemented in several ways. So operating systems, how to implement busy waiting. From the following section, you will be able to learn several methods in. Okay. So first method is something called disabling interrupts. We disable the interrupts. What is interrupt?
Interrupts are problems, distractions.
Yes, you can block and do something. Interrupt. Ongoing process, you can interrupt and do something, correct? Yeah, disturbing or stopping. So each process will disable all interrupts. So it is something like now, while I am conducting this lecture, I may receive phone calls, or I'm in the my office. Someone would come and enter for some other work, right? So as HOD, I have to attend so many other matters. So that is something like interrupting me. So I can disable interrupts. For example, I can lock the door, so no one can enter while I'm conducting the lecture. Or I can put my phone into silent mode or something like that. So that means no one else can interrupt, right? So disable all interrupts so that I can continue my lecture. But certain interrupts I can allow if I want. For example, I allow you to ask questions. That is also a kind of interrupt. But certain interrupts in operating systems, it depends on the situation, may allow. Now, disabling interrupts method means each process will disable all interrupts, okay? Just after entering its critical region. So once you are in the critical region, so it is something like if you go to toilet, you can't answer a phone, otherwise you will forget others are waiting. Yeah? So you have to disable all other interrupts. If it is critical region means other processes are waiting for that. And once you finish critical region, you need to re-enable it so that notify others you are leaving, right? Sometimes in case if you can lock the toilet door and go away, you know it's going to be a problem for others, right? So you need to re-enable them just before leaving. Those are the conditions, okay? When you disable interrupts. So when interrupts are disabled, no clocks can interrupt you. Like your CPU, there are clock interrupts. So once your time slot finish, there's a clock interrupt telling your time is up. You have to go away and give chance to another process. But this disabling interrupt option can even block that interrupt. No, I'm not going to stop my processing until I finish this critical section. Okay. So that way we can disable interrupts for certain cases. The CPU switches from one process to another only by the result of a clock or other interrupt. The CPU, when processing something, it switches from that process to another when there's a clock interrupt or another interrupt. Once the process disables the interrupts, what will happen? It can examine and update the shared memory without any problem, as other process cannot come into the shared memory. If other processes are not executing at CPU, they are not going to access the shared memory. So that way you can solve this problem. Okay. Can you think what are the disadvantages of this? You disable interrupts.
We need to have a lot of memory because once we are running process with disabling interrupts, it allocates all the memory. So in that case, to run another process, we need to have more memory.
No, this happens when only when it is executing in the CPU. You disable interrupt. So the shared memory part used by this process cannot be accessed by other processors, but only it is in critical region only. So that's why once you leave in, you have to re-enable that. That means you open up that shared part to others. Only when you are in the critical region, only when there is processing the CPU processing, only you block shared memory part. Others cannot update while you are using it. Okay. So
Okay.
that problem will not occur, the one you mentioned. But any other,
But while we are running such kind process, other process have to wait.
yes. Yeah, but it will solve a problem, no? Even with little delay for others, rather than facing sharp problems. No? Yeah, so it will slow down a little bit. Yeah. Let's say what they say. This method is unwise because if the user forgets to turn on the interrupts, so your software programs, this can happen due to a bug. If you forget to turn on the interrupt, then you are blocking the memory, right? Or the disable interrupt part, if you forget to turn on, then it will be the end of the system, right? Because you have disabled the clock signals, other process cannot enter to the CPU. So it is going to be a problem if there's a error, bug in your program. And also if there are two or more CPUs disabling interrupts, when you have multiple CPUs, right? So disabling interrupts affects only the CPU that executed the disable instruction. This is multiple CPUs. Okay. There are two or more CPUs. This process, that means disabling interrupts, affects only the CPU that executed the disable instruction, not the other CPUs. Therefore, other ones will continue running and can access the shared memory. So if you disable interrupts for only one CPU, other CPUs doesn't know about that. So processors running in other CPUs might access the shared section. So this may occur in parallel computing, or when you have more than one CPU, not single CPU, right? So these are two possible problems or disadvantages in disabling interrupts. So let's see another method of handling that. That is known as lock variables. So we'll have lock. This is a software solution. Like toilet door, you can have a lock, no? So no one else can enter once you lock. So same principle we can apply using software solution. This is a software. It contains shared variable called lock. So we define shared variable called lock, which is initially 0. Initially 0 means it is not locked. If it is 1, that means someone is inside the critical region, right? So when a process wants to enter the critical region, it will check the value of lock variable. Okay. If it is 0, it will change the value of the variable into 1 and enter the critical region, right? So you check the the lock variable whether it is 0. If it is 0, you can enter, but you have to make sure change variable to 1, because if another process come and check, they should know you are in the critical region. So if it is not 0, when you check the variable, if not, it will wait until it becomes 0, right? So that's the normal procedure. So if the door is locked, engage, you have to wait until it becomes open, right? The free. That concept also, this is called lock variable. Concept is easy, but how to implement? So to implement this, there are two concepts. One is semaphore, the other one is monitor. Okay, that's why we need to learn these two. So let's say what semaphore solution is. These problems discussed long ago. You can see in 1965, Dijkstra proposed this solution. So he proposed new variable type. It contains two operations. So semaphore solution contains two operations known as down and up. Okay. So down operation on a semaphore checks to see if the value is greater than 0. If so, it will decrement the value by 1 and then continue work. Right? So if it is 1, it will decrement it 1, that means make it 0 and continue the work. If the value is 0, you can't decrement now. The process is put to sleep. You are not allowed to enter without completing the down for the moment, right? So if it is more than 1 only, you can implement the down operation. If it is 0, you have to wait. That means sleep mode without completing the down operation, right? Now here, check-in value, changing it, and possibly going to sleep. So these operations must be critical, right? Because our earlier example, like when you check in the value of this Spooler directory and changing it caused the problem. So to avoid that, these three operations, this is all done as a single indivisible atomic action. So we call this atomic action. You can't divide it. Indivisible atomic action. Right? So it is like one command we are implementing all three. In between, no other command can implement. So this semaphore, this is the condition. We define these three as indivisible atomic action. Therefore, once the semaphore started its operation, no other process can access the semaphores until the operation is completed or maybe blocked. So others not allowed to access. The up operation increments the value of the semaphore at rest. Increment in the value and waking up one process is also indivisible. That means once you finish the critical section, you call the up operation. Okay, it is also defined as indivisible. Semaphores will be used by the processors to access the critical region without occurring race condition. So you can avoid race condition by applying this semaphore principle. Final semaphore variable can obtain integer as well as a Boolean values. So Boolean value means only two, like 0 and 1. But you may define it as integer value so that it can go like for up to 5 or 10 or like that. Right? But same principle. Okay. So that's the principle of semaphore. So I hope it is clear. If not, you have to read it carefully again. And the reference books also explain the semaphore and monitor examples. Okay. Then the second one, monitor. So you can see it's been proposed about 10 years later. Earlier one, 1965, right? The semaphore solution. So monitor solution is something updated one. Right? Hall and Prince Hansen, 2% proposed a higher level synchronization. Primitive called monitor. So monitor is a collection of procedures, variables, and data structures. It is something like when you learn this object-oriented programming. Right? Objects are collection of procedures, data, variable, and like that. Similar concept. Monitor is a collection of procedures, variables, and data structures that are all grouped together in a special kind of module or package. Processors can call the procedures which are inside the monitor, but they cannot directly access the monitor's internal data structure from procedures declared outside the monitor. So you can access. This is very similar to your object-oriented concepts, I think. I think you have learned those by now, right? So it's like protected or private data you can access only through procedures in the data structure, not outside procedures. So same concept. They cannot directly access the monitor outside the monitor. So inside monitor there are procedures. If you want to access data, you must use those procedures. So that's the concept. Okay. So monitors have important property that makes it useful for achieving mutual exclusion. Remember, we are going to achieve mutual exclusion. The condition. No two processes are allowed at the same time. Right? Only one process can be active in a monitor at any instant. So you can define your monitor like that. Only one process can be active in a monitor at any instant. It consists conditional variables along with two operations. What are the two operations? Weight and signal. Very similar to up and down in the semaphore. This one has two operations called weight and signal. From the weight operation, it causes the calling process to be blocked and allows another process that had been previously prohibited from entering the monitor to enter now. So calling process you ask wait, but block process you can allow in the previously prohibited from entering, right? You can allow it to enter. Wait signal. Now signal statement will be appearing. So wait and signal. Signal statement will be appearing only as the final statement in a monitor procedure. So once you finish, you can signal. So you can read chapter 2 in Modern Operating Systems, Tannenbaum. Or you can download, or you want me to share the Tannenbaum. Yes, I have chapter 2 PDF. I could download, and if you want, I can add. So this is from 3rd edition, but you find now latest editions. Process schedulers. About threads. We talk about user level and kernel level threads, and those diagrams and pop-up threads as well. Critical regions. So these are the 4 conditions. Old race condition. These are time diagrams like process A and process B when executing. So process A enters critical region here, but process B not in the critical region. But if B trying to enter the critical region, now it is occupied by process A. So B attempts to enter critical region, but not allowed. B is blocked, right? Until process A finish its critical region. A leaves critical region. So until A leaves, you have to put a flag, like wait, something like that. Once you finish A leaves, you can remove the flag, so no change the variable so that B can enter. So this is idle time for B. We have to wait to enter the critical region, because critical region allow only one process to process. Not all process can enter the center. So once B finish, we leaves critical region, so any other process can enter the critical region. So that's how mutual exclusion using critical regions. Mutual exclusion. There are some program codes how you can implement. Now there are examples like producer, consumer, program. So I want you to go through those. So producer, consumer means producer produce, consumer consume. So if no products are there, consumer cannot consume. No? So it's a problem in it's a typical problem. You can see how they implement in semaphore, then producer consumer performance in semaphores, then another one called mutex. With the implementation, then the monitor. So you can see monitor example, you have variables like integer condition and procedures like producer procedure, consumer procedure. So that structure. So you need procedures to access variables inside that, or data inside that. Monitor tool. So what I do is try to share that chapter 2, add it into your LMS chapter 2 of Tannenbaum's book. So you can go through them slowly. So I want you to go through the examples and possibly there's one interesting problem called dining philosophers problem. Right? So this problem means the philosophers. So imagine there's 5 philosophers. Philosophers are great thinkers, no? So sometimes they forget about the real world when they are thinking about certain problem. So there are 5 philosophers in a room. So time to time they come and sit in this dining table to eat. Now, unlike our Sri Lankans, they are Western philosophers. So how they explain this is this called a spaghetti noodles like thing. Yeah. When you sit and if you want to eat, now you can see two forks beside the plate. So they are Westerners. They are not using hands to eat like this, right? They only use forks. And the second condition is you can't eat noodles with only one fork. You need 2. So when you sit on one chair in this table, round table, you can eat only you pick both forks. With one fork you can't eat. Now can you imagine the problem?
Yes.
If 2 persons come and sit beside, එක ළඟ වාඩි වුණත් මොකද වෙන්නේ දෙන්නේ? You can't have 2 forks, no?
Yes.
Yeah. Since they are philosophers, they don't know they are sharing the same forks with 2 persons. Because their mind is something else, thinking about some problem. So this type of a table, this is a typical problem, and we used to test different software programs. So how can you write the program using semaphore or monitors to solve this kind of situation, this problem? You have to meet those 4 conditions. Remember the last condition? You can't keep one starving without allowing to eat. Yeah? So everyone should get at least one chance. Otherwise, that person will die. No? So maybe not a fair chance, but at least one should get like per day at least one chance of eating. Yeah? But sometimes one person may eat more than one, maybe 5-10 times. It doesn't matter. But you have to make sure at least everyone getting a chance. No starving. So you can see the problem from this diagram. You can read the problem. If you search for dining philosophers problem, there are so many examples, explanations about the problem. So there are program codes how you implement. So here you can see take fork procedure using down and up. You can see down and up the matrix variable. Right. So I have shared this chapter. You may go through it leisurely. That was dining philosophers problem. Another problem is readers and writers problem. Remember, I asked you to think about, we are sharing the same document. So if 2 persons wants to write at the same time, how do you solve the situation? So you can use this down and up mechanisms. You can use, you can try to solve readers writers problem using that one, the monitor approach or semaphore approach. So this for you to, it's an exercise for you to try. Okay. So getting an interrupt, you can hear a phone ringing. It's a bit far away from me. Anyway, let's go back to our, okay. Now we are talking about IPC. What is IPC? Inter-process communication. So following section, you'll be able to learn 2 popular inter-process communication problems and their applicability in the real-world computer programs. So one is readers, writers problem. So this one, which models access to a database, if it is shared database. Let's take airline reservation system, for example. You know, airline reservation, there are many agents trying to reserve the seats of a aeroplane. Right? All over the world, they are existing. So if 2 persons trying to access the book the same seat, we get the similar problem. No? So shared database. So we assume there are many competing processors wishing to read and write. Even though several processors can read the database at the same time, If there is a process which writes data into the database, and then none of the other processes can access the database. So reading is not a problem. You should not block reading, because then there will be a huge delay. So real-time systems like this airplane reservation, you can't block it. So you can consider local examples like cinema ticket, cinema hall. You can book using internet, no? Or through different agents. So when you try to book, before you decide, you have to see the available seats first. So if one person is reading, if you block it, others will not be able to read. Right? Therefore, reading should not block, because there are many persons read it, but not a book. It's like when you go shopping, not everyone buying the items. So it's okay to display. But if two persons try to buy the same thing, then only the problem will occur. If two persons try to book the same seat, so you have to address that one. Writing process, you have to use this kind of protection mechanism, mutual exclusion. So you can apply semaphore monitor concepts. So you can try to implement this. So your next assignment is, I want you to try this using any of your programming language. Okay? So you can read this and get the algorithm or how to implement. You can use, so what languages you are using now? Your programming assignments?
In second semester we studying C#.
Yeah.
First semester we study C++.
Right.
Basic things.
So any of the program language doesn't matter. So if you have this kind of problem, even your projects, you can select this kind of systems where we have critical regions, and try to see implement. This is going to be a good exercise for you to learn these concepts. So try to implement. So there can be many questions. So the question here is, can we write a program for readers, writers? Answer is yes, yes you can. You can write an effective program by using semaphores. According to the solution, the first reader gets access to the database. When it is changing the status of the database semaphore to down, then subsequent readers merely increment the counter. RC means read counter. When readers leave, they decrement the counter, and the last one out, it will change the status of the semaphore to up. So RC counter keeps number of readers. Therefore, semaphore will block the writers to get in the database. So now problem is, let's say 10 persons reading this same location. Now if one try to write a class, so what do you do? If you allow writer to change it, those 10 readers reading it become obsolete, not correct, right? So you need to find a logic. So either you have to update all 10 readers already read the web, or before you update it, or you have to wait all readers close and not allow other readers to open while others closing, and allow the writer to write and then allow them to read, right? So as a consequence, as long as there is a steady supply of readers, so if we wait, watch and read count, what will happen? There's a continuous supply of readers. Readers are coming again and again. So those who wants to book the seat cannot book, because while readers are there, you can't book now. So how do you solve that problem? Steady supply of readers. They will all get in as soon as they arrive, because you can allow readers to come while others reading. But writers will be kept suspended until no reader is present. Therefore, sometimes writers will never get in. You see the problem? Hence, when a reader arrives and the writer is waiting, what should you do? When a reader arrives while writer is waiting, you can suspend the reader. The reader is suspended behind the writer instead of being admitted immediately. So you can apply that logic. Therefore, a writer has to wait for a readers already in that were active when it arrived finished, but does not have to wait for readers that came along after the writer. So you put other readers in a queue, not allowing them if writer is waiting. Okay. That's one approach. So you can think different ways of implementing. And the dining philosopher's problem. Again, this Dijkstra proposed solution using Xenophos for that. Here is the story. 5 philosophers are seated around a circular table, right? You remember the diagram. With a plate of spaghetti. Between each pair of plates, there is a fork, and the philosopher needs 2 forks to eat spaghetti. That's the condition. A philosopher needs 2 forks to eat spaghetti. Each philosopher consists of an alternative periods of eating and thinking. So they have alternative periods of eating and thinking. Sometimes they eat, sometimes they think. When a philosopher gets hungry, she or he tries to acquire her left and right fork one at a time. You can select the order, right? Not both at the same time, but you pick one first, then select the next one. If successful in acquiring 2 forks, she eats for a while. So it's a lady philosophers. Huh? So if successful in acquiring 2 forks, she eats for a while, then puts down the forks and continues to think, finishing the critical set. In the above problem, the main concern is, can we write a program for each philosopher that does what is it supposed to do and never get stuck? That's the idea. Never get stuck. Alright? So you can think about that. Answer is yes. As the solution, we need 3 semaphores. And it uses an array state which keeps track of whether a philosopher is eating. So you need to keep track of philosopher whether he's eating or thinking or hungry. Hungry is the you want to eat. Blocking state, waiting state. Philosopher may move only into eating state if either neighbor is eating. Philosopher's L is philosophers' neighbors are defined by macros left and right. So you can have left and right variables. Same situation can occur when several processes competing for exclusive access to a limited number of resources in a computer. So that's why we are learning this. In operating system, same situation can occur. How? When several processes are competing for exclusive access to a limited number of resources. We have limited resources like our shared memory, right? Or CPU, or printer, or whatever. Okay. Is it okay up to now? So your exercise, try your own language to implement one of those. Dining philosophers, so readers, writers, book. So I want all of you to read it, otherwise you won't get the feeling of what this is. You have to try by yourself. Just reading will not help. Maybe your next assignment could be a program and the results. Another section is deadlocks. Want me to explain today or shall we do it next week? That's another topic. But it's not that long, so we'll try to. I'll try to introduce. Remember that traffic junction situation, forecast block junction. That's the deadlock situation. So lesson 3 we have explained it. The deadlock situation can occur in a computer system. Let's take the following example. Assume 2 processes A and B. Okay. Need printer and a scanner. So A and B try to access printer and scanner to carry out a specific task. So what will happen at the beginning? Process A grants the print and starts processing, and process B grants scan. Now process A is using printer, process B is using scan. At the middle of the process, now process A using printer, B using scan. In the middle, process A requests the scan. Now process A currently using the printer, but it needs something to scan and print. What will happen? And also process B requests the print. Now process B is in the scanner, but it needs to print something scanning while scanning others. So both requesting the resource used by the other. Okay. But none of the requests will be granted. Why? Now when process A while using printer, it is requesting the scan. But scanner is busy with the B. B is not granting scanner until B will finish its task. So process A has to wait, right? Similarly, process B while using the scanner, it wants to print something. But printer is blocked by the A. So process B while blocking scanner waiting for printing. Process A while blocking the printer waiting for scan. Can you imagine that situation? So it's a deadlock situation. No one is releasing the resource. Right? Requesting resource is already obtained by another process. Due to this reason, process A, B will be blocked. Process A, B will be blocked and will remain as it is forever. This situation is called deadlock. Okay, so that's an example for deadlock situation. So we don't want such situations in our computer systems. So if you understand the problem, now we can think about the solution. So processors can request and grant two types of resources. So resources we can define, one is preemptible and non-preemptible. So what is preemptible? Preemptible resource can be taken away from the process only if it knows side effects. So you can forcefully take away. Right? So when process say while using printer needs a scanner, you can take away a scanner from process if it is preemptible. So memory is an example. If you define it like that, okay. So memory is an example for preemptible resource. Non-preemptible resource cannot be taken away from its current owner. Like critical section, you can't take away, right? If it is non-critical, of course you can take, right? So you have to address this problem. So Hoffman in 1977 mentioned 4 conditions should be there to hold a deadlock situation in the computer environment. So when do you get deadlock situation? Certain conditions. First one is mutual exclusion. We already discussed mutual exclusion. No? What is it? Each resource is either currently assigned to exactly one process or is available. So this is mutual exclusion. We allow only one to use it. So you can avoid the deadlock situation if you use this. Second one, hold and wait. What is that? Process currently holding resources granted earlier can request new resource. So this condition is known as hold and wait. So you granted some resources and it can request new, like you granted printer to process A, but process A can request scanner also. That is known as hold and wait. And it is not releasing the something you are holding, not releasing the printer, right? So if you do not grant same permission to process B can't hold and wait. After a while, it should release the resource so that process A can continue and avoid deadlock situation. Okay. Third method is no preemption. Resources previously granted cannot be forcibly taken away from process. So we define it like that. They must be explicitly released by the process holding. Like process A, we can mark as preemptible. It is not releasing, but B, we can mark it as non-preemptible. Then the fourth one is circular wait. there must be a circular chain of 2 or more processes waiting for a resource held by the next member of a chain. There must be a circular chain of 2 or more processes waiting for a resource held by the next member of the chain. So it's a kind of circular way of checking. So if 2 or more processes waiting for a resource, they can check periodically in the resource. If it is available, they can check the waiting members in a circular way. So these four types can will be used to handle deadlock situation. Sorry. Now, you may have deadlock situations due to these, and you can avoid them. There are 4 strategies to address deadlock situation in your operating systems. First method is, so you won't get deadlock situations always, right? Only when they access critical sections. Once in a while, you get it is something like traffic junction. You are not always getting deadlock situations, so just ignore the problem altogether. Right? In this method, it will just ignore the problem as nothing has happened to the system. So somehow they solve. That is one way of handling. Then the second method is detection and recovery. So time to time we can try to see whether there's any deadlock situation anywhere and recover. This method will not prevent deadlocks from the systems. Instead, it lets them occur. It allows deadlocks to occur, but time to time check and recover. Then it tries to detect and take some actions to recover the system. For example, your computer system, sometimes you get the message, no, this application is not responding. Wait or exit, like that message. So when they detect such kind of block, you can give the option to the user. That is one method. So that is detection and recovery. Third method is dynamic avoidance by careful resource allocation. So when you're allocating resource, you can carefully allocate to avoid them. From this method, it will allocate resources among the process in such a way that the deadlock will not occur within the system. But thing is, you need additional intelligence for this. That's the disadvantage. So all above methods you allow deadlock. Last one is prevention. As 4 conditions need to be fulfilled to occur for deadlock. Preventive methods will be taken to make sure even one of the conditions will not fulfill in the computer system. So to have a deadlock, the 4 conditions mentioned earlier, these 4. So if you make sure these 4 conditions, if you handle properly, you can prevent the deadlock situation. So when you design operating systems, you can do like that. Right, that's it. So explain the applicability of classical IPC problems by taking a suitable example. You can take dining philosophers problem or readers writers problem. But I want you to implement it and using any language. So this is a bit complex lesson. That's why I want you to try interprocess communication. So we have completed learning lesson 8. This lesson we have discussed the basic concept behind inter-process communication and two classical IPC problems. They are those two problems, Dining Philosopher and Reader's Writers. Then an introduction to deadlock will be given to you. So next lesson we will see lesson 9 to be able to learn different types of scheduling with different scheduling algorithms in detail. Okay. So there we can stop today's lecture.